All right, perfect. All right, really excited to be here. Thanks, Ron. Thanks, Justin, for allowing us to talk about this RSA ceremony MPC protocol that we started implementing at Ligero. This is, the presentation I'm going to give is mostly sort of the technical aspects of this. I'm going to keep it at a high level, but they're the technical aspects of this. I should say that the names here, my colleagues Karmeet Hazai from Bar-Ilan University and Abi Shalat from Northeastern University just across the river. All of us part of Ligero, where we are trying to implement this RSA protocol. This slide doesn't do justice to some of the people behind the scenes, like Abi's students, Jack, Isa, Schuler, Megan, who's here, and one more, Yash. And of course, the engineers at Ligero, Nick, Tarek, and Yuri, two of them over here. Anyway, so let me start. So what's the goal? So the goal is, we've heard a lot about VDFs, like RSA-based VDFs. We want to compute an RSA modulus n using an MPC. So the parties are going to interact, and they're going to compute a biprime n. A biprime meaning n, a product of two primes. The secret key is basically the factors. You don't want to reveal these factors, otherwise the security of all the systems that we want to base on this modulus is going to go out of the window. And finally, why do you want to use MPC is because you can do this in a nice way where parties can generate this modulus, and with very little sort of post-processing can erase all trace of what was used to compute this modulus, specifically the two prime numbers that were used to generate n. So the goal here, let me say, of course, this is an engineering one. We knew multi-party computation since the 80s. You can take any computation you want. We know how to do it. The feasibility was established. But the goal here is we want something that we can implement to run among 1,024 parties. Moreover, the security we want is n-1 security. This means that you want your protocol to be secure in terms of both correctness and privacy, even if 1,023 parties get corrupted. In other words, all you need for this protocol to be secure is one honest participant. And why are we doing this? You've heard a lot of talks today about where this is headed to. You want to compute verifiable delay functions, inherently sequential computations. And this is a classic construction of one such candidate. And of course, there are newer constructions which extend this idea. And the goal, at least again, to just emphasize, is we want to produce this modulus n so that people can use these cryptographic primitives. And of course, there is a lot of applications. There are companies that want these things, and as Ron said, you don't know how technology is going to be used. And right now there are plenty of applications for VDFs in the blockchain space. All right, so how are we going to do this? Secure computation. I'm going to assume sort of most of you know at least a little bit about what secure computation is, and not going to go into the definitions. You basically have a set of parties who have their own inputs and want to compute jointly some function over their inputs. And the two basic properties you want from this protocol is that they learn the output of the function correctly on some set of inputs and learn nothing more. Okay? All of this can be like very rigorously mathematically formulated, but this is sort of the goal, and this is going to be enough for us to generate this RSA modulus. So let me start with the, I'm going to jump straight into the set of protocols that are used to do multi-party computation, specifically for the generating an RSA modulus. So it all started, I would say, the first paper that sort of opened this area and considered this as a task was by Bonnet and Franklin. And I should tell you, till today, the framework established in this is what is being used in all implementations, including what I'm going to talk about, what we are doing here. So when they considered, they had a framework, and they sort of they envisioned a scenario where there were some set of parties where you have honest majority. And again, I'm assuming all of you familiar with sort of blockchains, what honest majority assumption means. So this was sort of a theoretical framework and a multi-party computation protocol to generate the RSA modulus, and since then there has been a lot of works. The initial set of works like Poupart and Stern, Gilboa, Algersheimer et al., all of them were sort of theoretical frameworks trying to improve the security aspects of this, semi-honest to malicious, and I'll tell you a little bit more about these things later. Number of parties, number of corruptions. But the last two works actually went ahead and even did implementations. And I should say that they did implementations in the two-party setting. And while the work of Hazai et al., which was in 2012, took like a few minutes to do for two parties, the recent work of Fredrickson et al. In Crypto 2018, they showed how to do it in two parties for even reasonable parameters within seconds. But none of them have actually implemented in the multi-party setting, meaning more than two parties, which is what we're going to talk about today. So let's start with I'm going to tell a little bit about, some history on these protocols very briefly, and then we're going to jump into the Bonnet-Franklin framework on how we are going to do this task. So the Bonnet-Franklin protocol basically proceeds in 3 steps. In the first step, people are going to generate, or they're going to pick shares for both primes P and Q, meaning P is going to be the sum of the shares of the parties, Q is going to be another sum of the shares of the parties, and P and Q are going to be the candidate primes. You're going to first sample this, you're going to multiply them in a secure way to generate the modulus, and then you're going to test whether the numbers that I picked initially, were they 2 prime numbers, and the product being, and n being a product of 2 primes. Okay? And here, there are many ways. We all know the classic Miller-Rabin primality testing. This paper actually introduced something called the biprimality testing, where you can directly find out if n is a product of 2 primes. And we'll see what are the implications of the two tests. So there was another work. I want to say this sort of qualitatively stands out from the list in that, so this also sort of has the same kind of steps. You pick candidates, you multiply them, you do some trial divisions to pre-sieve some of these bad numbers. If it's already divisible by 2 or 3, like you can figure this out easily. You do some pre-sieving of your candidates, you multiply them, but then you actually check the individual numbers that you chose were primes rather than the product or the candidate modulus being a product of 2 primes. Okay? So you have P and Q, the 2 candidates. You check, is P a prime, is Q a prime? If both of them are a prime, then I'm going to say, okay, use this modulus. So this sort of stands out in that. And let's say that, so in how they do the primality testing. All the other works use the biprimality framework of Bonnet-Franklin, but this work said, let's just do the standard primality testing that we all know from our algorithms class. And so what is that? I mean, well, if you just want to do the basic Fermat test, you want to compute a to the p minus 1 and check if it's 1 mod p. Now, why is this? Okay, this is okay, except that you want to do this securely. And as I mentioned to you, you never want to reveal P and Q in the clear. I mean, that was the whole point of this ceremony, that I want to produce this modulus without showing or sharing what the individual primes are. Okay? So here, I want to compute a to the p minus 1 mod p. Now, I have to do this securely, meaning I have to do this when p is in a shared form. And this is inherently a very inefficient operation, to do modulus reduction over a secret number. Okay? And here is sort of some state of the art in terms of MPC. You should just look at the second line over here to do some simple RSA operations securely using, I should say this is based on Boolean circuits, so take it with a pinch of salt, but still with the state of the art Boolean secure computations, the communication, this is even just between 2 parties, is like 3 terabytes. So using generic multi-party computations for these modular reductions over a secret number is not going to be something that's going to scale well. The work of Hazai et al. Actually, moved towards, understanding, okay, this computation is really arithmetic. Let's use arithmetic primitives to do these things. Actually, they used the pi-a encryption, which is sort of additively homomorphic, which I'll talk about it. They used this sort of an approach, but they still sort of had the, the same kind of flavor of selecting primes, perceiving them, multiply, and then doing the biprimality testing. But this was the first work that even implemented and showed that you could do this between two parties. The most recent work in the space is due to Fredrickson et al. From crypto last year, where they actually used some sort of, I want to say, Boolean circuit technology for doing this computation. They used what is called an oblivious transfer-based protocol. And again, I'll talk about this in a few slides down. I sort of want to mention that this, this primitive oblivious transfer, or OT, is like very, very fast now. That if you trace sort of what's been done in the last 6, 7 years, it's like now it's very close to being like a symmetric primitive. And let's talk about what we are going to do here. What is our protocol blueprint? Just with every other MPC protocol that we've been tackling over the years, it proceeds in 2 steps. You first provide a protocol that is secure against a benign adversary called a passive adversary, semi-honest, or honest but curious. There are many names for this. These are participants who are willing to follow the protocol to the T and not deviate, but after the computation wants to try to learn more than what they want to. Okay? So in other words, here you're worried more about privacy against these benign adversaries, and then you amplify the security to get full security, or security against malicious or active adversaries. So these are the 2 basic steps that we are going to follow. And I sort of want to say that several works in multi-party computation, what they do is that they sort of directly try to attempt to get a malicious protocol. They use sort of ad hoc techniques to get this malicious security. And our approach, at least, which we've found is quite successful, is to find first sort of a really clean and good passive protocol, and then think about generic techniques to amplify it to malicious security. Okay? So quite like for most of the part, what I'm going to do here is talk about how do we get a good passive protocol, and then at the end, I'm going to go against what I just said, but I'm going to tell you how we get malicious security. All right, so we are now in search of a good passive protocol to do RSA modulus generation among 1024 parties. So let's start with the, we said first you're going to sample some few prime numbers, some candidates, and then you want to multiply. So let's start with this operation of just multiplication. What we want is a primitive that's called secure multiplication. It says that if 2 parties have 2 numbers, they want to multiply and get shares of the result. They don't want to know the result. If you know the result and know one of the factors, you know both. But the point here is that if you have 2 numbers, you want to multiply them and get sort of 2 numbers, C1 and C2, such that they sum up to the product. Okay? And you want such a gadget to do. This is called a secure multiplication. And what's being used, again, in the Fredrickson et al. Paper is actually an approach using an oblivious transfer. So what's an oblivious transfer? It's a very, very simple gadget. You have 2 parties, sender and receiver. The sender has 2 strings, S0, S1. The receiver has 1 string, B. And the goal is for the receiver to securely learn SB, meaning it should not learn both values. It should learn the value that it's choosing, like it chooses B and it should learn SB, not the other one. And the sender should learn nothing about the receiver's bit. Okay, it's a very simple primitive. Think of it as a multiplexer if you know from architecture. You want sort of a secure version of this thing. And I mean, this very simple gadget already is very powerful. We know already that this is sort of complete for secure computation, meaning if you can do this securely, you can do every computation securely using a multi-party computation protocol. Right now, we have very, very fast implementations. There are these things called oblivious transfer extensions, where at the beginning, you do a few public key operations, and the rest of them are sort of like just symmetric key operations, and they are very, very fast. So let's see how can we use this gadget to do actually multiplication. Okay, so this goes to the work of Gilboa from '99. And the idea basically is you want to multiply, typically you want to multiply over some ring or field, some some domain. Let's say that you want to multiply in z2 to the L. Both the participants are going to take their inputs A and B, and the receiver in the oblivious transfer, which is on the left-hand side over here, is going to actually take the binary representation of the element A. It's going to be L bits. If it's a z2 to the L element, it's going to be L bits. And they're going to execute L oblivious transfers. And in these L oblivious transfers, what essentially they're going to compute is the product of that bit with the input of the other party. So this can be executed with an oblivious transfer because, you know, if I have my input 0, I know what you should give me. If my input is 1, I know what you should give me. Okay? But you want to do it securely, meaning you don't want the answer, but sort of shares of the answer. So you run this protocol bit by bit. You just do bit multiplication on one end with the entire string on the other. And then you can actually, there's a simple realization at the end that the answer that you care about is sort of a linear combination of all these answers. It's actually like, you know, 2 to the I times the ith oblivious transfer. And now if you sum this up at the end, you get that the sum of the final answers is the product that you're looking for. Okay? So high level here is that you can do multiplication. If you want sort of L bit number multiplications, you have to do L oblivious transfer. Each oblivious transfer, you know, incurs some communication cost. It's going to be roughly, if you have, you know, L OTs with L bit numbers, it's going to be roughly L squared. But the amount of cryptographic thing, you can reduce it to like the security parameter. The total number of bits you send will be L squared, but in the oblivious transfer, you need to only send sort of a seed to an encryption key and, you know, do something better. Anyways, bottom line is it's like quadratic in what you want to sort of achieve in this computation. Now, a second building block, which is more suited for arithmetic operations, is a slight generalization of oblivious transfer, and this is called oblivious linear evaluation. Okay? And the generalization is like, you know, OT is for bits, OLE is for field elements. So one party, the sender, has A and B, the other party has X. The receiver wants to learn AX plus B. Okay? It's a quick exercise. If you think X is a bit and you think of that as a string, you can show that OLE reduces to OT for the bit case. So we are going to use, or at least this is the primitive that we are going to use for doing secure multiplication. Now I'm going to tell you how easy it is to sort of implement such a primitive if we actually have something called an additively homomorphic encryption. Now we all know there are even fully homomorphic encryption, but here we're just talking about a simple additively homomorphic encryption where, you know, if I have encryptions of A and B, just operating on the ciphertext, I can get an encryption of the sum of the plaintext. Okay? Now, how does this work? How do I, if I had such a, actually I need a public key variant of this thing, which is again easy to get. You want to, let's say that I have a public key version of this additively homomorphic encryption to get an OLE. What you do is the receiver picks, you know, generates a key pair, encrypts its input, sends it to the other party. The other party, now, just using the public key and the encryption, actually can compute encryption of AX plus B, which is what you want to, the other party wants to learn. But why? Because everything is a linear operation. A times encryption of X is like adding encryption of X A times, you get encryption of AX. And since it's public key, you know how to get encryption of B. You add it, you have encryption of AX plus B. And, you know, the sender returns this to the receiver can decrypt and learn the answer. Okay? The encryption is going to give you the necessary privacy properties for this computation. But as written over here, this is only semi-honest or honest but curious. Okay? Now, why haven't people used OLEs? Well, I mean, it is, if you think of it, the cryptographic operations has widely been believed that OLE is typically slower than oblivious transfer. We have, you know, the ones that people use in practice are, you know, PAE or the other one that I'm going to talk about. But now, recently, there's been a lot of progress in getting really efficient batched versions of OLE. What is a batched version? Well, you know, if the sender and receiver have many, many inputs, A1, B1, A2, B2, X1, X2, ... they can, in one sort of interaction, learn for each of these instances the result of the OLE. Okay? And here I want to sort of quote what a good friend of ours, I don't know if he's in the audience, but says is that LWE, which is this lattice-based cryptography assumption, which is called learning with errors, actually it has tremendous influence in getting something called a fully homomorphic encryption. And a lot of people are working to make this efficient. But whether or not this is going to be the case, LWE definitely, hands down, gives the best additively homomorphic encryption scheme. And specifically, they have this this batching sort of phenomenon to get this sort of throughput for additively homomorphic encryption. And that's what we're going to use. Actually, we're going to use a slight different variant called threshold additively homomorphic encryption for our system, because we're not looking at a 2-party setting, we're looking at 1024-party setting. And a threshold version sort of makes this computation in a distributed way. Okay? So in a threshold additively homomorphic encryption, you have 3 basic operations. You have a key generation, which is sort of in a distributed way. You generate a single public key, and you have shares of the secret key. And encryption is just, it's a normal operating procedure. You just encrypt using the public key. Decryption, again, is distributed. Each of them distributes, gets a component, you add it up, and again, I'm hiding a lot of things under the rug, but in essence, this is sort of what is happening in a threshold additively homomorphic encryption. I should sort of say here that there is sort of a chicken and egg thing happening here. The whole goal here was a setup ceremony for the RSA where you wanted to generate this n, which was the product of 2 primes. And here I'm saying, well, I need to generate a public key for an additively homomorphic encryption, which is again another distributed protocol. So where am I going to go next? And well, it's not that bad. The ones based on lattice-based cryptography, there are much simpler ways of just simple addition with randomness can help you generate such keys. Okay, so it's not complicated to do this distributed key generation procedure. So with this primitive threshold additively homomorphic encryption, I'm going to give you sort of a bare bones of how we will do this multiplication in a distributed way. Okay, so we have n parties. Each of them have shares for the 2 different candidates of the prime, P1 through Pn and Q1 through Qn. Your goal is to compute the sum of Pi's times sum of Qi's. This is what you want. Okay? And you want to do it in a secure way. Each of them want to protect the privacy of their Pi's and Q's. So what are they going to do? First step, they're going to do the distributed key generation, and they're going to get the public key and shares of the secret key. Okay? Next, they're going to encrypt their Pi's. They're going to now broadcast this. Okay? And the goal of the broadcast is so that they add up all these encryptions to get the encryption of sum of Pi's, which is encryption of one of the candidates that we want. Okay? It's an encrypted form, so no one knows what this prime P is yet. So the next step is going to be everyone is going to compute Q times this encryption of P that they just received. Now, given that this is additively homomorphic, this simplifies to encryption of P times that number. Okay? You're going to broadcast again. And this time, you're going to sum the broadcasts to get encryption of sum of QIP. Okay? Take P out as a common factor. This becomes encryption of P times Q. Okay? And now, this is the modulus you want. You can do distributed decryption, where everyone decrypts locally, provides it, broadcasts it, you sum it up, and you get P times Q. Okay? So using a threshold additively homomorphic encryption, you have the simple task of multiplication that you can do very nicely and very efficiently using such, if you had a good threshold AHE scheme. Okay, so this is sort of what we're going to do for multiplication. Now, let's talk about the serious bottleneck in this computation is actually sampling candidates. And I'm going to argue this. So the first step, we said, look, we're going to get many, many samples of these Pi's and Q's, multiply them. But the main bottleneck is going to be this number. Can someone tell me why I have put this fraction?
Density of primes.
Density of primes. If I want to generate a 1024-bit prime, roughly the probability that a candidate is 1 over 1024. And if you use the biprimality testing, because we don't want to use the Miller-Rabin, you want a number that's a product of 2 primes, and the probability of that happening is 1024 squared. And the communication alone is going to kill you if you wanted to do the MPC. So it's a good idea. I mean, previous approaches have done this pre-sieving, but the pre-sieving is still not going to be good enough because you have to generate that many numbers and eliminate them, okay? But still, it's nevertheless a good idea. When I sample numbers, can I eliminate the ones divisible by the first few primes, okay? 3, 5, 7, so forth. And this is what has been done before. People have used additively, like PyA encryption to do this sort of pre-sieving for certain basic primes. I'm going to talk about the one that's based on oblivious transfer. Again, this is a very simple approach introduced by Fredrickson et al. I don't know if they introduced it, but anyways, I'm going to tell what they used in their paper. How to, given a candidate maybe shares of a number, can I find if it is divisible by a small number, 5 or 7, okay? So what do you do? So you have two numbers, you have a number p, and you have shares p1 and p2 with the participants. They want to find out if it's divisible by 7, okay? What are they going to do? They're going to do a slight extension of oblivious transfer. Instead of 1 out of 2 oblivious transfer, they're going to use 1 out of 7, okay? And it works exactly the same way. I said it's a multiplexer. I choose which one I want. In 1 out of 7, I give a number between 1 and 7, and I pick one of them, okay? So that's a 1 out of 7 oblivious transfer. Now, what is the goal of this protocol? Well, the goal is actually twofold. One, I do want to find out if it's divisible, because if it's divisible, I want to eliminate it. But if it's not divisible, I don't want to know any information about what you had, right? I mean, you want to protect P1 plus P2. So this protocol should still be secure in that sense. So what you're going to do is you're going to do this 1 out of 7 oblivious transfer where, the right-hand side is just going to put random numbers, M1, M2, M7, okay? And the left-hand side, they're going to use R1, which is P1 mod 7. They're going to take this number R1, and they're going to select the R1th element in your list, okay? So this would be, let's say that R1 is 5, I will learn M5, okay? Now, if P1 plus P2 was divisible by 7, it's 0 mod 7, which means if this side was holding R1, the other side is holding minus R1. Okay? So what will they do? So after you do the oblivious transfer, the right-hand side is going to just give minus m, or you take minus of R2 and give m of minus R2 to the other party. Now, if the m I received and the m that the party gives me in the clear match, then it means R1 is minus R2. And it means it was divisible by 7, and I discard this candidate. But if it was completely different numbers, then I know P1 plus P2 is not divisible by 7. Okay? So by a simple 1 out of 7 application of oblivious transfer, I can eliminate a candidate if it's divisible by small numbers. I say small because you have to do 1 out of that number. When you go to 733, it's still possible, but it's still a lot. Okay. So how do these previous works do? So they have this pre-sieving method. They have candidates. They check divisible by 3, 5, 7, 11, so forth for how many ever primes you want to do. And then if one of them fail, you discard the number. And this does not reduce the number of candidates you have to pick. You still have to pick that many numbers, and you're going to eliminate them. But the one thing it does help is that you don't need to wait until the product has come to find these things, but the individual numbers can be eliminated, okay? So we don't want to do this. We are going to use something slightly different, and here I want to sort of say a really, very cool idea of Abhi's, and let's say Abhi's team as well, is that instead of generating numbers and sieving them, is it possible to just generate numbers that are already not divisible by some prime numbers? This would be great because I already sort of eliminate a huge chunk of numbers that I'm going to sample. So a constructive rather than destructive approach for generating these numbers. So question?
Well, so theoretically, if each person was responsible for picking a number mod that prime that's not 0, you could you could use Lagrange interpolation.
You're almost there. It's going to come now. So it would be nice, as I said, if your numbers were sort of pre-approved by the first set of prime numbers. What he was hinting at is the Chinese remainder theorem. Okay? if you already have, so Chinese remainder theorem sort of says that there is an isomorphism between numbers, in mod z, product of relatively prime numbers, and the product of these spaces. And roughly speaking, multiplication in one domain translates to multiplying, in each of these individual spaces. Now, for us, what we care about is that each of these individual spaces are mod that number, okay? And you don't want numbers that are 0 mod that number, because you want it to not be divisible by this. So if I had to pick a number that was not divisible by the first set of primes, me individually I can do this, but we have to do this in a distributed way. But me individually we can do this by, I'll pick a random number mod n1, n2 that is not 0, okay? And then I'll do the interpolation or the Chinese remainder theorem reconstruction, and I'll get a number that's not divisible by the first set of primes, okay? And now there is a simple observation that follows immediately, is that if I had to, instead of, now I said P, we were thinking of it as sum of numbers, sum of shares, I'm going to move to multiplying, okay? So if I had P as P1 and P2, two participants, now I want to think of multiplying P1 and P2 to get my candidate prime P, rather than adding. Now what happens is that if P1 and P2 individually were not divisible by these first set of numbers, if I do a multiplication, I'm going to get a number that is not divisible by these numbers if I do the multiplication modulo n1 through nt, okay? So this is a very cute trick. It's an idea where each of us now, instead of doing addition, we can do multiplication. We pick each of us, make sure that our numbers are not divisible by the first set of primes, and then we can do this, okay? So basically here there are two approaches. One is this multiplicative shares that I was saying. Each of us will pick numbers not divisible, multiply them to get the candidates. We have to do still secure multiplication. This hasn't changed. But there is again yet another trick where I can do the same with additive shares, okay? And I won't get into it because I'm running a little late. I just sort of want to say there is a trade-off between these two approaches. If I did multiplication, remember I have to do this securely, and there is some sort of interaction that will happen. If I have to multiply 1024 numbers, the number of rounds will be log this, okay? But if I did addition, I can squash this at the price of increasing the communication a little bit, okay? So there are trade-offs in both these things. It depends, like, we are going to implement this. We're going to see, look, where exactly is our trade-off going to sit, and sort of use that approach. So where are we now? So we've done secure multiplication. Now instead of pre-sieving, we're going to get it to be pre-approved. We're going to pick the first set of primes. How many primes do you need? Well, you want primes so that n1 times n2 times nt is at least 1024 bits, okay? Because when you multiply, you want that property. So now what has happened? We started off with 1 over 1024. Now where are we? Well, we can show that if we eliminate sort of the first until like 827 or something prime, then the probability that a candidate is 1 over 60. And now when I select two numbers, multiply, and then do the biprimality testing, it's sort of like 1 over 3600. So which means roughly I have to get like 5,000 candidates with an expected constant number of rounds to sample an RSA modulus, okay? Now, the three parts of the Bonnet-Franklin framework were sampling numbers, multiplying, and then the biprimality. So we are not going to do much change with the biprimality testing, and I'm not going to go much into the details. There are two basic steps. There is a first step that is you want to pick a random number gamma with a certain Jacobi symbol and compute some exponent. And the second is to compute the GCD of n and p plus q minus 1. The first step can be done sort of publicly. We can sample gamma publicly and do these things. Not much, you don't need any cryptography. The second part, you will require, again, threshold additively homomorphic encryption to compute the GCD of n and p plus q minus 1. And this is it. Now, I should tell you that this is not going to be the bottleneck of the computation, because after we generate many, many candidates of the candidate moduli, I can already check if n is like, I did pre-sieving only up until 1 prime. But then after, I can go to a lot more numbers, and I would have eliminated more of these candidates. So the number of candidates that are going to survive to the biprimality testing is not going to be too much. So, and so in this, I've just copied this from the FLOP paper, and they say that you have to do this S times. You actually, in practice, you don't have to do this S times. And in fact, even like Miller-Rabin test, it's enough for like very, very large numbers. You just need to do it like a couple of times. It's not something that you, and actually there's a lot of work that shows that for very large numbers, I don't have to repeat it many times. And the same holds for the Bonnet-Franklin test as well. So far, what we have done is we have come up with the best passive protocol for doing distributed RSA modulus generation. The next step, and the last few slides over here, is going to be how do I make it malicious? And in the beginning, I made a big spiel about saying, oh, I want to use very generic techniques of taking a passive protocol and making it malicious. I have some works in this area. Come and ask me later. I can tell you more about it. But here, we are actually going to do something different. But first, I'm going to tell you some works before that have done how to amplify security specific to the arithmetic setting. So using the OLE primitive between two parties to get malicious security, there is a work. This roughly says, well, I need to do 22 OLE operations per multiplication in my computation. The overhead is roughly 22. That's how you should read it. From semi-honest to malicious, the overhead is roughly 22. The OT-based approach, again, already you have some blow-up because you have to do these finite field multiplications. But then to get malicious, again, there is an overhead. And there are some very specific assumptions-based constructions for secure arithmetic. But in general, the overhead is like pretty high. But what we are going to do actually is something much better. And I sort of want to say that this RSA modulus generation is sort of simpler than generic MPC computations. In generic MPC, like secure multi-party computations, you are worried throughout about the privacy of your input. In some sense, what if I used my social security number, if I used, I don't know, my medical data? During the computation, I really care about, like, nothing should go wrong and nothing should be revealed. But here, actually, it is randomness. Now, if something did go wrong, as long as I catch it, I can restart the computation, kick the person who did something bad, and restart the computation. So I don't need to know until the end if anything wrong has happened. So in the RSA case, this is because I truly don't have private inputs a priori to the computation that I want to protect. Okay? So what we are going to do is back to the classics. We're going to use the classic GMW paradigm, which says if I want to go from semi-honest to malicious, use zero-knowledge proofs. In other words, at the end of the protocol, all participants are going to prove that they did their things correctly. Now, I should say that a lot of like what we've done started off from our work from doing zero knowledge, and I should say, I don't know how much of you are aware of this. Definitely in the blockchain space, you do know. Zero knowledge proofs, practical implementations have improved leaps and bounds. And we are going to use one of the works from our team to implement this zero-knowledge protocol. I'm going to just quickly give you the highlights of the zero-knowledge protocol. It's sublinear. It does not require any public key operations. If the number of multiplications in your circuit is some number n, we need to use, like, our communication is something like square root 10 kilobytes. And what we need to prove in our computation is actually a very, very simple statement. At the end of the computation, you've done all these modulus, you've generated all these moduli, and at the end, let's say one of them wins and says this is a biprime. Now, I need to prove in zero knowledge only that this particular instance I did correctly. All the others that failed, I don't really care. I can just reveal my randomness to show that I did things correctly. But the one modulus that was approved in this whole process, I need to prove in zero knowledge that I did actions correctly. And primarily, the actions here are related to the encryption scheme. The final thing I'm going to say sort of is that in our architecture, we are going to employ a central coordinator. And this coordinator is just going to help with broadcast. Typically, if you have to do broadcast, it's like quadratic communication. But if I had a coordinator that can do some of these computations, it becomes linear. If you recall in our protocol, everyone encrypts PI, sends it, and you sum it up, and then you give, and then everyone wants to know encryption of P. Now, everyone can give that to the central coordinator. The central coordinator can sum it up and give it to everyone. So you squash quadratic communication to linear communication. Okay? But I should say here that as much as we are employing central coordinator, one should ask what is the threat model. And the threat model is that you don't need to trust anything about the central coordinator. The central coordinator will not learn anything about the inputs. It's just doing the simple addition computation. Okay? And you don't need to worry about correctness because this can be verified later as well. Okay? So here I'm going to quote one of these things that Ellie says is that with these things, it used to be the case that trust but verify, but in this case with the coordinator you don't have to trust and you can verify. All right, so I already mentioned all the broadcasts here can be reduced. There are 3 broadcasts. It can be reduced from quadratic to linear. Okay, and this is our protocol. You generate threshold keys. You sample pre-approved prime numbers. You multiply them using threshold additively homomorphic encryption. Do the biprimality testing, and finally, for the one that succeeded, you prove in zero knowledge. Okay. So these are, Justin already mentioned this. These are sort of our targets. We want 1,024 parties, roughly 120 megabytes upload and download. We want the number of rounds. Again, we are implementing and we want to know what is going to be the bottleneck. Is it communication or computation? My belief is that it's going to be communication because you have 1,024 parties. And we want like very lightweight clients. And the coordinator can be heavy because we can implement it and we can have like a really a big machine for our coordinator. And with that, thank you. Questions or lunch? Yes.
So if you ban parties that are trying to sabotage the protocol, is it not possible to join the multi-party computation without like some form of KYC? So is it perhaps possible that...
So we get n-1 corruption, but if you're going to say what is sort of one thing that if...
I keep trying to abort the protocol.
Yes. So this is sort of a fact of life, not fact of anything else. If you want n-1 corruption, you're not going to get liveness. If one party aborts, the protocol stops. But of course, this is something that we will discuss more during the afternoon session. This we've had. Our goal here is to give you an n-1 secure protocol, but we'll facilitate things we'll catch cheaters. That's what is more important than anything, because if someone aborts or someone, we want some good mechanism to kick them out of the computation and restart. Yes?
So is it possible to have like an Ethereum smart contract that verifies the hero proof?
Yeah.
And you put a security deposit, and then when you submit the proof of correctness, you take it back?
Absolutely, yeah. You can make it incentive-based, yes.
Okay.
Any other questions?
Do you worry about the distribution of the parallel primes, or do you not care too much about it?
So actually, that's actually a good point. One thing that I really pushed under the rug was that I said finally I had these numbers mod these product of primes, but when you add them, you're going to add over integers. And this will skew the distribution. I don't know if this is what you mentioned in terms of... So you can do that. But, yeah. There's enough primes, yeah. Oh, no, okay. All right, thanks.